So section 6.3 part 2, our next example is example 3. This time they give me a picture, which is kind of nice. It says a rectangle is inscribed. Inscribed means totally inside a circle of radius 2. Let P be a point in quadrant 1. This is the vertex of the rectangle. Again, vertex is quadrant and is on the circle. Express the area of the rectangle as a function of x. So let's get their picture drawn. So we have a circle. We know that the radius of the circle is 2. And sitting inside that circle, sorry, is a rectangle. My circle's not very good. It's a good thing you have a picture, right? And the rectangle hits the circle at some generic point x comma y. We also know the radius is 2. Okay, and they want us to find the area of the rectangle. Well, we know that the area of a rectangle is its length times its width. So what we have to do is figure out what the length and the width are in terms of the picture. Well, if this is again the point x comma y, then this little distance sitting right here is x, and this little distance sitting right here is y. And hopefully that makes sense from the previous work. However, we need the total length of the rectangle. Well, if it's sitting right inside and it is centered, then this distance is also x. Well, that means that this distance is also y. So our overall length is going to be from here to here, which is 2x. So the area in terms of x is going to be 2x for the length. And we're going to pick up 2y for the width. So a y here and a y here, and x here and an x here. Or 4x comma y. We still have the same issue. To write a function in terms of x, the only variable on the right-hand side we can have is x. So we're going to need to get rid of the y. This time they did not give me a backup equation to substitute in for. We're going to have to figure out our own equation. So we're going to backtrack to what the circle is telling us. We know that the equation of a circle is x minus h quantity b squared plus y minus k quantity b squared is equal to r squared. Well, this circle is centered at the origin. So h and k are 0. And the radius we know is 2, and 2 squared gives us 4. So here's a second actual equation. This is a function. This is an equation because it's actually equal to something, not equal to just the function notation. So what we're going to do is solve this for y in order to eliminate over here. So we're going to solve for y because we need to substitute in for y. So we can do that pretty quickly. Y squared is going to be equal to 4 minus x squared, and you'll square root it. And because we're dealing with a geometric formula, we will not need the plus or minus on that solving. We need to square root it. So we're simply going to replace our y with the square root of 4 minus x squared. So we end up with 4x times the square root of 4 minus x squared. There it is. There's your area of that rectangle in terms of x. So if you know how far over you are to put that point on the circle, you then know the area of that rectangle. So pretty slick. You'll see a lot of these both in this class for calculus and calculus classes. So they're pretty famous. I don't know, infamous maybe is the better word, which is quite a few of them. And again, the goal eventually is to take that area formula and maximize it. So how big of a rectangle can I put inside the circle? Example 4 is a little more complicated. It says Metro Media Cable is asked to provide service to a customer whose house is located 2 miles from the road along which the cable is buried. The nearest connection box for the cable is located 5 miles down the road. So they gave you a picture. Let's see if we can make sense of that picture. So over here is the cable box. Here's the house. And we know that this is 2 miles and this total distance is 5 miles. So we could run the cable along the road and then straight up to the house. So you'd run it the 5 miles and the 2 miles. You could also run the cable directly over the land without going along the road. The problem is that that's more expensive. So it goes on to tell us if the installation cost is $500 per mile along the road. So 500 per mile. If you go along the road, you dig the trench and then bury it back in once you lay the cable. It's $700 a mile if you go over the open land, so off road, which should make sense to everybody. It's more expensive because you're going up and down hills, you might be going around trees. It's more expensive to go off the road. We want to build a model that expresses the total cost of the installation as a function of the distance x in miles from the connection box to the point where the cable installation turns off the road. So the picture shows us They're going to lay the cable so far along the road, and then we're going to go off road. So this distance here, from here to here, is X. Okay, so our cost is going to be $500 per mile along the road. So 500 times the distance along the road. Wait, we know the distance along the road, that's X. They gave me that. Plus 700 for the distance off the road. Distance off. And there's the problem. We have to go figure out what that is. This guy's fine because it's already in terms of X. That part is not in terms of anything, so we need to figure it out. What we're going to notice is that over here, we have a little right triangle. And what we're looking for is the hypotenuse of that right triangle. We'll call it C. So we need A squared, B squared, C squared. We have A, C is what we're looking for, but we need this side over here. Well, we know this total distance is 5. If this is X, then this side of that right triangle is 5 minus X. So now we can use the Pythagorean theorem. We know that 2 squared plus 5 minus X squared is equal to C squared. So C is going to be equal to the square root of, just square rooting both sides. 2 squared is 4, and we'll clean that up a little bit. And 5 minus X squared. I'm not going to clean it up any more than that. Again, eventually you'll do things with derivatives and you'll have to do some cleanup then. But for us, we don't need to clean up stuff. So I'm going to bring that over here. So this is what we just call C. So our cost in terms of X is going to be 500X plus 700 times the square root of, and now I'm going to pick up this entire equation from over here, our substitution. So we have the square root of 4 plus the quantity 5 minus X squared. And there is our cost function for laying that cable. And this is an actual real world application problem. Then it goes on into part B. It says, okay, let's compute that cost if X is 1 mile. So in other words, if we only go 1 mile and then go off the road, how much is it going to cost us? So C of 1 would be equal to 500 times 1 plus 700 times the square root of 4 plus 5 minus 1 squared. So we can do a little bit in our head. That's 500. 5 minus 1 is 4. 4 squared is 16. 16 plus 4 is 20. So 700 square root of 20. And because this is an application problem, it's acceptable to go to the decimals because we need dollars and cents here. So what we really have is dollars per mile times the number of miles, dollars per mile times the number of miles. So we're going to end up with dollars as our final answer. And if you do that on your calculator, you end up with $3,630.50. And that's our final answer. So there's the cost. You can also do it at 2 miles and see what the cost is, 3 miles, 4 miles, and so forth. Ideally, somewhere in here is a place where minimizing the cost is going to occur. So again, we could graph this function on our graphing calculator. It's going to look something, I don't know, maybe idea what it looks like. I'm guessing it's looking something like that, not a true parabola, and it'll have a minimum. So you can go find that minimum on a graphing calculator to figure out where you need to lay the cable and how to do it.